You would like to test symmetry for both of the given equations here. And how do you determine individual symmetry? Let's say an x-axis symmetry. So let's start with the x-axis symmetry test. So in the x-axis symmetry test, we have to understand what x-axis symmetry is. X-axis symmetry means that if you reflect, if you negate basically the y values, you will have the same x value, right? That's what x-axis symmetry is, right? It means that a reflection through the x-axis is possible, right? And if you imagine xy plane, and you have a certain equation drawn like this. If you decide to reflect it through the x-axis, it must be true that it should look like this. Like this, right? So it means that it will be symmetric with respect to the x-axis. So what does that tell you? It tells you that for the same x value, you could have two possible different y values that are negations of each other, right? The negated versions of each other. So that leads you to understand that to test the x-axis symmetry for the given equation, you need to simply negate the y values, right? So you need to replace the y with the minus y and to see if you get the same result as the left side, right? So let's test that. So we're gonna leave the x squared by itself, and we're gonna add the negative y instead of the y, right? Because we're trying to negate the y to see if it will give us the same as the left side we have. So minus y will be squared instead of the y, right? So let's see what we get. X squared plus minus means minus y plus y squared, right? Because negative y squared is plus. Plus and plus is plus. So as you can see, this is a different equation. The left side does not match the original left side. This is not equal to x squared plus y squared, right? So this is not, this equation does not have an x-axis symmetry, right? Does not. So if you were to plot this in the xy plane, I'm not going to ask you to plot this in the xy plane. And this was an example. This is not the equation that we're looking for. This was just an example so you could see how this works. But in any case, this equation is not, the graph of this equation is not symmetric with respect to the x-axis. Now, let's test the y-axis symmetry. So again, I'm going to show you with an example on the xy plane how you can think of understanding what the y-axis symmetry is. So suppose that you're given y is equal to x squared in an equation like this, right? Y is equal to x squared. Notice that for the same y value, for the same vertical value, you will have two different x values that will lie on the same horizontal line. So that means for the same y value, you will have negated versions of the x values for this equation y is equal to x squared, right? So it makes sense because when you talk about y-axis symmetry test, you're essentially negating the x's and seeing if you get the same thing. Notice that if you negate the x here and then you square that, you will still get x squared, right? Because minus x squared, including the negative inside, is still x squared, right? And that shows that the negative x's, let's say when x is negative 2, it will be 4. It's just the same as the 2 was when it was squared. That was also equal to 4, right? So here, what tells you is that you have to take the given equation and you have to negate the x's this time to test the y-axis symmetry, right? So let's see, minus x squared plus y squared. What does that give us? That gives us x squared plus y squared, right? Because negative x squared is the same thing as x squared. So that matches the original left side, right? It doesn't change the equation. Bingo. So that means y-axis symmetry for sure. for the given equation. Now, finally, let's test the origin symmetry. Now, origin symmetry test, how does that work? How does that work? And again, let's use the xy plane to show an example. Notice that if I give you, for example, an equation, y is equal to x to the third, that looks like this, the famous one that you remember. Now, notice that origin symmetry means simply you're going to take the first quadrant. Notice that this indeed is symmetrical with respect to the origin, right? It's not symmetrical with respect to the y-axis, right? There's no continuation here. That is a mirror image. There's no mirror image through the x-axis either, but there's a mirror image through the origin, right? The origin means that you're going to look, you're going to treat the mirror image as the opposite quadrants, like quadrant 1 and 3 or quadrants 2 and 4, right? These call for the origin symmetry test, right? Opposite quadrants like that. So in this case, you can tell that there is, in fact, origin symmetry here, right? Because this is reflected, right, through the mirror image of quadrant 1 and 3, right? You can definitely tell this is symmetric, okay? So if this is symmetric, that means, notice that, how does that work with the x values? You have a certain x value, right? And you have the certain y value. The same thing here. You have a certain x value, right? Go the same distance to the left and the same distance down instead instead of going up, right? The same distance as we went up. So as you can see, this will be the same coordinates of x and y, except that they're negated, right? Both will be negated. The x and y here is minus x minus y, right? But the absolute distances for the respective x's and for the respective y's will be the same, right? So that means to test the origin symmetry here, you have to negate both the x and the y. All right? So now let's test that. So we're going to negate the x, and we're going to also negate the y, and see what that gives us. All right, so that gives us x squared minus y plus y squared. Now, as you can see, this does not equal the original left side, right? Because we have a minus y. X squared plus y squared, right? So there's no origin symmetry, right? So the only answer to this is that there's y-axis symmetry. Now, the next part is similar, right? Let's start with the x-axis symmetry. You already know what the graphs look like. You already know what the graphs look like. So it remains to go over this. The x-axis symmetry means you're going to negate the y's and see if you get the same left side. Times a minus y plus minus y squared. That gets us x squared minus xy plus y squared. Notice that this does not equal the original left side, right? Because we have a plus xy and here we have minus xy, right? Does not equal the original left side. And I'm going to circle that, as you can see, minus versus the plus, right? So there's no x-axis symmetry. What about y-axis symmetry? Y-axis symmetry test will require you to negate the x's and see if you get the same equation. Like that. This equals x squared minus xy plus y squared. As you can see, again, this does not equal the original left side. X squared plus xy plus y squared. Simply because, compare these two. There's a minus and there's a plus coefficient, right? No y-axis symmetry for this graph of this equation. Now finally, the origin symmetry. The origin symmetry requires you, once again, like we showed in the previous example, to see if you negate both the x's and the y's if you get the same left side as the original equation showed, right? So minus x squared plus minus x times y. I'm sorry, we have to negate the y's also, right? We're negating both. Plus negative y squared. So that gives us x squared plus xy this time, because both the x and the y have negative coefficients, plus y squared. Notice that this matches the original left side. Bingo, right? Right, so there is origin symmetry. So the first equation graph was only symmetric with respect to the y-axis. This equation graph is going to be symmetric with respect to the origin only. Okay? So I hope this was helpful. Thanks so much for watching. See you in the next video.